So we have to assign some original coordinate system to this. I'll come back to the given in a minute here. So for convenience, I'm going to say that x is right, y is up. In my original coordinate system, I have a tensile load on the x faces of 100 megapascals. And I have a compressive load on y of 75. So in the transformed state, I'm taking this cube and I'm going to rotate it 30 degrees clockwise. So we have to see where are the new faces located. So it was originally this way, and now I've rotated it 30 degrees and it's oriented along this direction. So that means that originally the cube was here, it's rotated here. This y, this is now the y prime direction. And again, it's 30 degrees from its original orientation. X was here, we rotated that down by 30 degrees. So this is the new positive x prime face. We have to be very careful of what we're assigning as our new positive faces, x prime and y prime, or axes, x prime and y prime. Again, we took this, we tilted it down 30 degrees. So x is now at x prime, y is now at y prime. And now on this rotated element, we want to see what are the stresses that are acting on it. So we can take our original stress state. I'll include this in the givens. We want to see originally what are the normal stresses and the shear stress with the correct sign on them. All right, so from here, what is our value of sigma x? Originally a tensile stress 100 megapascals. Okay, it's compressive, so a negative 75 megapascals. And then the shear stress in the original orientation. All right, so we have all the information we need, the original stress state for our plane stress condition. We want to see what stresses are acting on it when we rotate it 30 degrees clockwise. So this means our theta value is going to be a negative 30 degrees. Again, clockwise will be a negative, counterclockwise will be positive. Using our original information, we can go to these equations here and find what are the stresses on the new x prime, y prime face, and what's the new shear stress. Okay, so the stress on what I'm calling the new x prime face, I'm going to take the original values, so sigma x plus sigma y, 100 plus negative 75 over 2. Plus the difference, so 100, oops, this one's minus, 100 plus negative 75, 100 minus negative 75, this gives me the plus 75, times the cosine of 2 theta, plus tau xy sine 2 theta. Well, tau xy was originally 0, so I won't include that term here. Right, so calculating this out, the stress on the new x prime face, the normal stress on the new x prime face, I get positive 56.3 megapascals. Right, on the normal stress on the new y face, it will be the same 100 minus 75 over 2 minus 100 plus 75 over 2 cosine negative 60 degrees. Again, tau xy is still 0. So the new stress, negative 31.3 megapascals. So this will be still compressive on the new y face at this orientation. And now the new shear stress at this rotation, negative 100 minus negative 75, so 100 plus 75 over 2. Sine negative 60. And again, tau xy is 0, so that will drop out. So I want to take these values and now draw them on my stress element, my rotated stress element, 30 degrees from it clockwise from its original orientation. So starting with the sigma x prime, tensile 56.3. Again, that's on the x prime face, which is now down and to the right. I'll have that tensile stress 56.3. On the y face, the normal stress will be a compressive 31.3. So one thing to notice, in my drawings, none of these values will be negative. The sign is reflected by the direction they're going. So we got negative 31.3 here. That means it's compressive, so I draw it compressive, but with a positive value of 31.3 next to it. Since we have a positive 76, on positive faces, it's pointing along positive axes. So actually that means that we get this direction for our shear stress. A value of 76 megapascals.